Awake, for morning in the bowl of night has flung the stone that puts the stars to flight. And lo, the hunter of the east has caught the Sultan's turret in a noose of light. So begins one of the most famous of all poems, which is to say, the 19th century translation of the Rubaiyat of Omar Khayyam. The original version was written around the year 1120. More than 800 years passed before the poet Edward Fitzgerald converted it into English during the 1850s. The original doesn't actually have a title. Rubaiyat is simply a traditional Persian poetic form, a verse of 4 lines, typically in an A-A-B-A pattern, like the one I just recited. In English we call it a quatrain, from the French, and before that the Latin term for 4. The word rubaiyat comes from the Arabic ruba, which also means 4. And so it's entirely appropriate that we begin a discussion of mathematics in the Islamic Golden Age with this poem by Omar Khayyam. Without Edward Fitzgerald's extremely free interpretation of the Persian original, we'd probably not know about Omar Khayyam at all. Whether or not Khayyam ever wrote most of the verses attributed to him is a discussion I won't get into here. But in his lifetime, and for centuries after, Omar Khayyam was famous among scholars across the Middle East, not as a poet, but rather as an eminent mathematician. In this lecture, I'm going to touch on the work of a couple of mathematicians of global importance during the Islamic Golden Age, a period in history that ranges from roughly 750 to 1258. The most important name I'll discuss is al-Khwarizmi, a 9th century Baghdad-based Persian scholar, and a towering figure in the history of mathematics, whose expertise also reached into other fields of study, such as astronomy and geography. We'll also return to Omar Khayyam, who lived and worked in the Persian cities of Isfahan, Bukhara, and Samarkand, about 300 years after al-Khwarizmi was hard at work. The scientific legacies of these men is a bequest that benefited the next great flowering of mathematical inquiry in medieval Europe centuries later. But before we can begin to look at the mathematical achievements produced during the Islamic Golden Age, it's important for us to understand something about the state of mathematical knowledge at the outset of that era. The oldest extant mathematical texts come to us from the Babylonians and the Egyptians and are dated around 1900 BC. Although textual evidence is incomplete, math appears to have emerged as its own distinct discipline in China during the 11th century BC. It also appears that Chinese mathematicians were the first to come up with positional or place value notation using base 10, i.e., assigning a place for the ones, a place for the tens, and so on. The Babylonians also used a place value system, but they employed a more complex base 60 numerical system. Later, by about the 6th century BC, the ancient Greeks turned mathematics into the subject we recognize today, which is to say, one dependent on deductive reasoning and proofs. It was also the Greeks, members of the Pythagorean school, who coined the term mathematics, from the Greek word mathema, meaning subject of instruction. Pythagoreanism, named after Pythagoras, the 6th century BC Greek philosopher and mathematician, was equal parts philosophical and mathematical. The 20th century English mathematician and philosopher Bertrand Russell said of Pythagoras, "It is to this gentleman that we owe pure mathematics, the contemplative ideal, since it led to pure mathematics, was the source of a useful activity." And who can forget Pythagoras' theorem, which is central to Euclidean geometry and its equation, a squared plus b squared equals c squared. The Arab world's interest in mathematics had already peaked during the Damascus-based Umayyad Caliphate, the second of the four major Arab caliphates that presided over much of the Muslim world after the death of Muhammad in 632, and which lasted from 661 to 750, just prior to the onset of the Islamic Golden Age. The caliphs, that is, the Muslim world's chief spiritual and administrative leaders, employed Persian, Jewish, and Eastern Christian scholars to work with numbers, from simple arithmetical matters to more esoteric applications, such as astrology. This interest in mathematics expanded and grew under the powerful Abbasid Caliphate at the height of the Golden Age. With the Abbasid dynasty's founding of a new capital in Baghdad in 762 and a new centre of learning, the House of Wisdom, before the end of the 8th century, successive Arab caliphs employed the best scholars money could buy. The late American professor of history, Carl Boyer, writing in his History of Mathematics, makes the point that the Arabic miracle lies not so much in the rapidity with which the political empire rose, as in the alacrity with which, their tastes aroused, the Arabs absorbed the learning of their neighbours. Not least because of its practical everyday applications, mathematics has always been of central importance in all civilizations. But during the Islamic Golden Age, we saw astonishing advances in all fields of maths, not least algebra. To better illustrate this, I'm going to talk about a man whose very name is at the heart of algebra and algebraic calculations. He is Muhammad ibn Musa al-Khwarizmi. And the word algebra comes from the title of one of his books, the compendious book on calculation by completion and balancing. Now, the Arabic word for completion, in the sense of restoration or fixing, is al-Jabr, from whence algebra. Just to be clear, al-Khwarizmi didn't invent algebra. Babylonian, Greek, and Indian mathematicians were all known to be solving algebraic equations long before al-Khwarizmi was. But the nature of al-Khwarizmi's book on completions, the Al-Jabr, makes him central to the adoption and application of this discipline. The compendious book on calculation by completion and balancing would be translated from Arabic into Latin twice during the 12th century by two of the most important translators of their day, the Italian Gerard of Cremona and the Englishman Robert of Chester. It was a revelation to educated Europeans, and every well-stocked library would have had a copy. Al-Khwarizmi also wrote an important atlas and gazetteer, a corrected version of Ptolemy's 2nd century AD work, Geography, which, among other things, gave locations of cities and other important places in the known world. Now, Al-Khwarizmi's updated version not only corrected errors in Ptolemy's work, but added places not in the original that were now important in the Muslim world. For instance, Ptolemy didn't include Mecca, which in his day was an irrelevant desert town, and Baghdad, the Abbasid capital, with a population approaching 1 million, didn't exist when Ptolemy was writing. Al-Khwarizmi's geography reached Europe in around 1400, and in Latin translation was of vital importance for European explorers, including one Christopher Columbus. So it's easy to see why Al-Khwarizmi is known as the first Muslim geographer. But now let's return to the beginning of our story. Born in modern-day Uzbekistan in around the year 780, Al-Khwarizmi was a Persian scholar who did most of his work in Baghdad's House of Wisdom, or learning centre. Like most of his fellow scholars at the time, Al-Khwarizmi didn't work exclusively as a mathematician. Indeed, the more formal divisions between academic disciplines with which we're more familiar today simply didn't exist at that time. So, for instance, a serious scholar would be expected to work in the fields of maths, chemistry, medicine, philosophy, literature, and of course, Islamic theology and Quranic studies. It's one reason why we encounter so many polymaths from the Islamic Golden Age. Such broad knowledge was expected of a scholar. In its simplest or elementary form, algebra began life in the form of symbols that were employed in place of numbers. By manipulating these symbols, one could make calculations to discover hidden or unknown quantities. Al-Khwarizmi says in the introduction to his book on algebra that it possesses the mathematical skills such as men constantly require in cases of inheritance, legacies, partition, lawsuits, and trade, and in all their dealings with each other, or where the measurement of land, the digging of canals, geometrical computations, and other objects of various sorts are concerned. Interestingly, when the word algebra first entered English via Latin in the 15th century, it was used to describe the medical procedure for setting broken or dislocated bones. Only in the 16th century did the term come to be associated with its own branch of mathematics. Until then, maths was divided into arithmetic and geometric fields. So the addition of algebra as a distinct branch of mathematics shows its great importance even then, and of course, as its applications have grown, even more so today. The first part of Al-Khwarizmi's seminal work lays out the mathematical procedures required in algebra, that is, the algorithms, or means by which we can solve equations. The second half of that book is full of practical examples, and it's here that Al-Khwarizmi deals with the applications of algebra, discussing in detail the sort of everyday problems it can solve. And for me, it's here where Al-Khwarizmi hits the bullseye. Instead of filling his pages with the very symbols used to solve equations, Al-Khwarizmi instead takes the readers through the process in plain Arabic, written out in longhand, not the shorthand of algebraic symbols. In this way, he made algebra accessible. To paraphrase Gilbert and Sullivan's very model of a modern Major General, not only was Al-Khwarizmi well acquainted with matters mathematical and understanding equations, both the simple and quadratic, but he opened this dimension of thinking to the non-mathematical mind as well. Al-Khwarizmi, says the British theoretical physicist and author Jim Al-Khalili, was the first to abandon the practice of solving particular problems. Instead, he provided a general series of principles and rules for dealing with mathematical problems by breaking equations down into a set of steps, which of course is the algorithm. By explaining the procedure in general terms, Al-Khwarizmi demonstrated that the method itself could be conceived as general in nature, thereby allowing the reader to approach other algebraic problems by applying that general procedure. Stated otherwise, this is how Al-Khwarizmi made it possible for algebra to exist as a subject in its own right, a distinct branch of mathematics, and not just a technique for manipulating numbers. One of the monographs Al-Khwarizmi wrote, which proved highly influential in the introduction of his algebraic concepts, outlines the two principal operations he employed to solve equations. They are al-Jabr, meaning the transposition of terms from one side of the equation to the other, and al-Mustaqbala, meaning the cancellation of equal terms when they appear on opposite sides of the equation. So, al-Jabr turns the equation bx plus q equals ax squared plus bx minus 3 into bx plus q plus 3q equals ax squared plus bx. And al-Musqabbala turns it into 4q equals ax squared. If all this talk of algebra and quadratic equations makes you want to run away, you can relax. Because now I'm going to turn my attention to numbers. We're so used to the numbers we use in our daily lives, from 1 to 9 plus 0, that it's hard to imagine using any other counting system on a regular basis. I don't mind telling you that I was terrible at maths in school. I might come out at the top of my history class, but bottom for maths. It simply didn't click for me for the longest time. I even tried decimals, but didn't see the point. However, when it came to the more obvious, practical applications, my interest in the subject grew from there. There's nothing like calculating foreign exchange rates in Arabic to make you start paying attention to numbers. That said, if I'd had to use Roman numerals instead of what we now call Arabic numerals, life would have been much harder. Roman numerals might have served their mighty empire well for hundreds of years, but they have several disadvantages over the numbering system we're all more familiar with today. One obvious disadvantage is that Roman numerals look like letters of the alphabet. And although they can be distinguished from the alphabet by the line across the top, that doesn't make calculating with them any easier. Also, there's little correlation between the amount of Roman numerals written down and the size of the number. So, for instance, 2000 is represented by two M's side by side, while 1988 requires 11 separate letters. Now, if you're trying to work it out, the answer to how an ancient Roman spells 1988 is MCMLXXXVIII. It might look great at the end of the movie credits, but it's a nightmare when trying to do a quick addition while you're out shopping. Also, the 7 basic letters used in Roman numerals function only up to the number 5000, after which one needs additional special symbols. That can be a problem, especially for billionaires. Finally, but fundamentally, Roman numerals don't have 0, and Hindu Arabic numerals do. These numerals were invented in India at some point between the 1st and 4th centuries AD. At that time, all things Indian in the Middle East were referred to as Hindu, and the numerals were not intended to represent any particular religious qualities. In the year 825, al-Khwarizmi wrote a book explaining the utilitarian advantages of Indian numerals and the decimal numbering system, and introducing them into the Middle East in a work that was probably called the Book of Addition and Subtraction, according to the Hindu calculation. This book likely was also the first on the decimal system to be translated into Latin by the great medieval scholar Adelard of Bath, some 300 years later. Adelard's text is untitled, although it's usually referred to by the opening words in the Latin, Dixit al-Khwarizmi, or Thus said al-Khwarizmi. And if that's not a big enough claim to fame, the Latinized form of his name, al-Khwarizmi, also gives us the term algorithm. In Europe, this text would get a more formal title only many hundreds of years later, in the 19th century, when it came to be called Al-Khwarizmi on the Hindu art of reckoning. This is the oldest known writing using a fully developed numeration system, according to the account Mathematics from the Birth of Numbers by the Swedish writer Jan Gullberg. However, Robert of Chester's 12th century translation of Al-Khwarizmi's work erroneously assumed the numerals to be of Arabic rather than Indian origin. That said, the Arabs developed 2 versions of numerals based on the Hindu model. East Arabic, which is the dominant form today, and West Arabic, which, although now extinct, closely resembles the prevalent European, and therefore American, versions of numerals in use today. Some of these are instantly recognizable in all three forms. The number 1, for example, is more or less a straight vertical line in all three cases. Likewise, the number 9 is clearly recognizable in the different languages, but that's about it. The most obvious and at first confusing differences are in the Arabic symbols for 0 and 5. In Arabic, the number 5 is represented by a small circle, like a 0, while 0 is indicated by a single point, which looks a lot like an English full stop punctuation mark. As an aside, although the Arabic language is written from right to left, Arabic numerals are arranged as we do ours, from left to right. Apart from the numerals themselves, the most important and enduring innovation that Muslim scholars adopted from Indian mathematicians, again via al-Khwarizmi's writings, was the concept of positional notation. This would prove to be of enormous importance for later Western mathematical advances. It's Pope Sylvester II who's credited with the introduction of Hindu numbers into Europe. Sylvester II was a French pontiff between the years 999 and 1003, who read and spoke Arabic thanks to his time studying at universities in Muslim Andalusia. Sylvester, like al-Khwarizmi 200 years before him, quickly understood the advantages of Hindu Arabic numerals and worked hard to introduce them to Europe. And it's because Pope Sylvester knew them from Arabic sources, and because Arab traders working in the Mediterranean also brought these numbers into Italian and other ports, that they became known as Arabic numerals. Of course, as one might expect, Sylvester's less educated and superstitious critics accused him of various offences, from being a secret Muslim to a devil worshipper. For some years, there was strong resistance in Europe to using what many people considered dangerous Saracen numbers. Now, let's examine the mathematical legacy we've inherited from the Middle East during the Golden Age. One man who would read and be impressed by al-Khwarizmi's book on algebra, the compendious book on calculation by completion and balancing, was the Italian mathematician Fibonacci. Often referred to as the greatest European mathematician of the Middle Ages, Fibonacci, in his own writings, quotes al-Khwarizmi again and again and at length. Born in Italy around 1170, possibly in the city of Pisa, Fibonacci travelled and lived in various parts of North Africa as a boy, notably in modern Algeria. His family made its living as traders, and anyone living in the Mediterranean basin at that time saw the sea as a bridge rather than a barrier to overseas markets. Fibonacci first encountered Arabic numerals in North Africa. Pope Sylvester's efforts to see their introduction to Europe almost 200 years earlier clearly not having been as successful as he might have hoped. And in 1202, when he was in his early 30s, Fibonacci published a book called Liber Abaci, or the Book of the Abacus. After the publication of this book, Arabic numerals really became popular in Europe. As Fibonacci argued, whether you're involved in bookkeeping, calculating interest or exchange rates, or converting weights and measures, Arabic numerals made it much easier, especially when compared to the former, frankly clunking system of Roman numerals. So clearly, the story of mathematics in this era didn't begin or end with al-Khwarizmi. After al-Khwarizmi, and a contemporary of al-Khwarizmi's named al-Kindi from Basra in modern Iraq, who was another early 9th century Arab polymath, or scholar with expertise in numerous different fields of study, the first to provide a clear and abiding definition of algebra as operating on unknowns using all the arithmetical tools in the same way that the arithmetician operates on the known. was a 12th century scholar named al-Samawal. Born into a Jewish family in Baghdad in around 1130, al-Samawal converted to Islam, although he kept this a secret from his family for many years, for fear of upsetting his father, who was a rabbi. Al-Samawal made a number of important, if not explicit, contributions. One pertains to mathematical induction, which, defined narrowly, refers to the inference of a general law from particular instances. More specifically, for our purposes, it is a means of proving a theorem by showing that if a general proposition is true of any particular case, then it is also true of the next case in a series, and then shown to be true in one particular case. And finally, there is the work of that other great Persian polymath, Omar Khayyam, whom we met at the start of this lecture. Born in Nishapur, Persia, in 1048, Omar Khayyam is best known in the West today for his poetry, when he's remembered at all. How many times have the following lines appeared in a book of love poetry or read aloud at a wedding? A book of verses underneath the bough, a jug of wine, a loaf of bread, and thou, beside me singing in the wilderness, O wilderness, were paradise now. Yet, during Omar Khayyam's own lifetime, when there were precious few references to him as a poet, he was regarded almost exclusively in the context of his mathematical and philosophical scholarship. His treatise on demonstration of the problems of algebra was one of the most important contributions to the field of algebra. Among other things, the treatise provides a systematic discussion of the solution of cubic equations using intersecting conic sections. Now, a conic section is the curve one gets at the point of intersection of a surface of a cone with a plane. Why is this important? Because rather than attempting to give a numerical answer, which had stymied his predecessors, Omar Khayyam provided solutions as line segments, a piece of a line bounded by two distinct end points. As such, this was the first systematic study and the first exact method of solving cubic equations. Victor Katz, in his book A History of Mathematics, offers the following observation. A complete history of mathematics of medieval Islam cannot yet be written, since so many of these Arabic manuscripts lie unstudied. Still, the general outline is known. Islamic mathematicians fully developed the decimal place value number system to include decimal fractions, systematized the study of algebra, and began to consider the relationship between algebra and geometry. They studied and made advances on the major Greek geometrical treatises of Euclid, Archimedes, and Apollonius, and made significant improvements in plane and spherical geometry. Now, in my view, there's no more distinct field of Islamic mathematics than there is of Islamic chemistry or Muslim physics. Various confessional groups down the millennia may claim otherwise, but science has no religion. When confronted with an equation, there is a right and wrong answer. In and of itself, mathematical and scientific truth is reason unalterable. At the same time, it's important to set aside prejudice that might deny the scholastic fruits that scholars working in the Arab and Persian worlds, especially 9th and 10th centuries, are fully entitled. Maths may not have religion, but their study and original research was encouraged and paid for by a succession of Abbasid Muslim caliphs and other regional rulers. And thanks to their enlightened support, the West benefits from Islamic scholarship in the same way as did the Muslim Middle East from the work of the Egyptians, Babylonians, Greeks, Indians, and others before them. It all adds up.